Hey, it's Dr. J. 5.3 today, the graphs of polynomials. I know I've been talking about this for the last couple video lectures, and we've talked a little bit about the graph and the behavior of graphs, but in this section, that's pretty much all we're going to be talking about. So before I actually start drawing any graphs, let's just talk a little bit about the theorems. So we have the real zeros theorem, because we will use these theorems to help us graph. So the real zeros theorem says that a polynomial of degree n has at most n real zeros. When we do the graph, the real zeros will be the x-intercepts where it crosses the x-axis. And then we have the Turns theorem. Which says that a polynomial of degree n, I'm just abbreviating deg for degree n, I'm running low on space, has at most n minus 1 turns, or turning points. And then, of course, you do have the converse of these theorems. If you read these backwards, you would say, well, if the graph had n real zeros, then the degree would be at least n, if you sort of read them backwards. And then vice versa with the Turns theorem. If you had n turns, then you would say the degree is at least n plus 1. And we'll get to that in a minute. But for now, I want to deal with the face value of these theorems, the initial statement of the theorem. And why do we, use words like at most and at least and things like that? Why can't you just say a polynomial of degree n has n real zeros? I mean, wouldn't that be nice if you didn't have to worry about whether it was at least or at most? And so the idea is this. If you have a nice polynomial, and the word nice is, of course, not a mathematical term. Nice, I just mean that when you factor it, each factor occurs once. So that's what I mean by a nice polynomial. So something like this, x minus 5, x plus 3, and x minus 2, or something like that. So that's what when I say a nice polynomial, I mean something that when you factored it out, you just have a very nice factorization. Everybody is an integer or a whole number. You don't have any exponents outside of any of the factors. You have something like this. This is what you would call ideal in the sense that when you apply these theorems, you don't have to worry about the at least or at most. If you drew the graph of this polynomial, now again, I'm just going to kind of go through this kind of quickly, but I don't need that big of an x-axis. Each of these factors would give you an intercept, so or a real zero. So you have your real zeros, or sometimes I just say zeros. For x minus 5, you get 5. So you'd have 1, 2, 3, 4, 5. Yeah. And again, I'll be more precise when I start doing the problems from the homework or similar type problems. For x plus 3, you would get negative 3. So over here, negative 3. Okay, also known as x-intercepts. And then for x minus 2, you get x equals 2. And again, I'm doing this with mental math. I hope with a nice polynomial like this, I don't have to show very much work. And so x equals 2 would be right here. Okay? So that's the first thing I would do, is I would plot the intercepts. All right? And then I would look at the end behavior. Yeah. The end behavior, if you multiplied this out, the right arrow would go up and the left arrow would go down. All right? So I would say as x goes to infinity, actually I should do negative infinity first. Y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. So that's your end behavior. It means the right arrow is pointing up, left arrow is pointing down. I get that from the fact that if you multiplied these all together, the leading term would be x cubed. And I don't care about the rest of the terms, blah, 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 blah. All right, I wrote that in green because you don't really have to do that. You can just do that mentally. All right, you can look at it x times x times x, that's x cubed. So you know that the right arrow is going up, left arrow is going down. Okay, and so this is degree 3. Yeah, the degree is 3. And so when you're graphing this polynomial, the theorem, really the at most is exactly whatever it is. So the degree is 3, n is 3, and there's 3 real zeros. Yeah, so the word in this case doesn't really mean at most. It means exactly. Yeah. And so that's what your graph would look like. So you would have a degree of 3, and you would get exactly 3 zeros. Yeah? And then for the Turns theorem, you have n equals 3. Yeah, the degree is n again. And then so n minus 1 would be 2, right? Here, let me write that out. I know I don't have to, but I will. N minus 1 is 3 minus 1, which is 2. So there's 2 turns. Right? And so in this perfect world here, you don't really have to worry about the at most and the at least. Look, there are 2 turns. There's one turn here, and then there's another turn here. Yeah, so there's 2 turns. All right. So it has 2 turns and 3 real zeros. Exactly what the theorems, think about my word there for a minute, exactly what these theorems would have predicted. Okay. The problem is this. Not every polynomial is going to be nice like this. Yeah. Some polynomials are not so nice. So what happens? If there are exponents outside of a factor, the behavior changes. And I'm going to call this not the end behavior, but the behavior near the x-axis changes. So let's look at how that could happen. So recall from chapter 3, if you had a function like this, very simple polynomial from chapter 3. Yeah, this would be a quadratic transformation, shifting it to the right 4 units. Remember, the left and right shifts are backwards. So if you see x minus 4, the opposite of minus 4 is positive 4, so you'd shift it to the right 4 units. So this is a quadratic. I'll just say quad. So that's because there's an exponent on the outside of the factor. Yeah. And so the graph looks like this. And I'm not spending a lot of time on these until I start getting really into it. I'm just doing a very rough graph. Just 1 point at 4. I probably would make a table and plot more points if we were doing it the way we did it in chapter 3. In chapter 5 now, I guess we've backed up to chapter 5. We're just doing these very rough graphs just to make sure that you have the shape right. Okay. And so look what just happened. Yeah, look what just happened. You only have one real 0. Yeah, it's only touching the x-axis one time. Yeah, that's because this factor occurred twice. And so this is what we call multiplicity 2. Yeah. The multiplicity was 2. That factor occurs twice. Look, if I wrote it out as a factored form, it would be x minus 4 times x minus 4. It means that the same factor occurs twice. We call this a repeated 0. Yeah. So even though there's only one real 0, it is repeated 2 times. The multiplicity is 2. Multiplicity. You can't read that, can you? Multiplicity. There, now you can read it. So that is a case in which the theorem says there is at most 2 real zeros, but in this particular case, it's not 2. There's only 1. And that's why we use the term at most. Yeah, there's at most 2. Well, yeah, there's at most 2 because there's 1. And 1 is at most 2. So at most really just means less than or equal to that number. Similarly, if we go back to chapter 3, we don't even have to change it very much. Suppose I have a cubic. Yeah. A cubic has multiplicity 3. Yeah. So multiplicity 3 means that this same factor occurs 3 times. Yeah. So there's one real 0, x equals 4, even though that 0 is occurring 3 times. And so we say one real 0 with multiplicity 3. We're saying that that particular 0 occurs 3 times, but in the graph, you don't write it 3 times. 1, 2, 3, 4. You only write it 1 time. So in the graph, it looks like it only has 1 answer, because it really does only have 1 answer. It's just 1 answer, and I'm going to copy the shape of the cubic. Yeah, so it's the cubic shape with multiplicity 3. So again, what does the theorem say? The theorem says there is at most 3 zeros, or 3 x-intercepts, however you want to think about it. But is there 3? No, there's only 1. Yeah? It just occurs 3 times. So it's at most 3, but it could be less than or equal to 3. In this case, it's 1. So this is what we call the behavior near the x-axis. Sometimes referred to as local behavior. So we have 2 types of behavior in a polynomial. We have what's called the end behavior. And we have the local behavior. You put together these 2 behaviors, the local and the end, and you get the entire behavior of the graph, both locally and globally, which is another word for end, like at the end of the day, at the end of the world. Okay, so that's how we're going to be attacking the graphs in this section, and we're going to pay very close attention to the multiplicity when we draw the shape of the graph. Okay, I will mostly be concerned with the x-axis. I will only be concerned with the y-axis in certain problems where the y-axis value is relevant to the result. So in 90% of the problems, the y-axis is irrelevant. We're not really paying attention to it, but there might be a few examples where we need that y-axis. I'll just save those probably towards the end of the lecture. Okay. All right, well, let's get on down the road here and check out what's going on. Let's do some examples. Let's start off with just some algebraic examples. Given the polynomial, find all real zeros and the multiplicity of each. So we'll just take a polynomial function. Something like that. Okay. So we like to organize these in a chart. Sometimes I give you more rows than you need. It's okay to leave some of the rows blank if necessary. All right, so let's find the zeros. We can do this all with mental math. All right, this is all done mentally. If you really want to write it all down, you certainly can, but you can do this all mentally. X minus 5, what's the 0? 5. Yeah, it's the opposite. X plus 2, what's the 0? Negative 2. You kind of know why we call them zeros now, huh? Because if you plug in 5, you get 0. Yeah? If you plug in negative 2, you get 0. And then for this one, if you plug in 1, you get 0. So the zeros are 5, negative 2, and 1. I don't care what order you put them in. Put them in any order you like. I will care when you draw the graph where you put them, but when you fill out the table, I don't care. Just fill it out. All right. And then now look at the multiplicity of each. Okay. 2. Which one is that? That's multiplicity 2. Yeah. So 5 has multiplicity 2. If you don't see a multiplicity, it's considered 1. Okay. 1 multiplicity 1. And then if you see a 3, it's obviously 3. Okay. Those are the most common multiplicities, 1, 2, and 3. Okay. So that's it for this problem. You can leave a row blank if necessary. And then the idea is that this tells you the shape. Again, this is the idea. So the shape of this one would be something like this, or maybe like this. We don't know yet, but we do know that because it's multiplicity 2, it's going to have the shape of a quadratic. It could be an upside down quadratic or a right side up quadratic. This is what we call the local shape or the local behavior. So anytime the multiplicity is even, it's going to look like a parabola. All right. If the multiplicity is odd and it's 1, then it's going to look like a straight line, or perhaps a straight line going the other way. I kind of made that one a little bit too angled. It's more like that. There you go. And then for multiplicity 3, the shape would look like a cubic or a reversed cubic. And again, this is just the local shape near the x-axis. If you want to see a graph, so the graph, actually I brought my graph board today. So let's go ahead and try this out. right. Now I am going to draw the y-axis, but I'm not really concerned with the intercept on the y-axis. Maybe I'll mention it before I walk away from this problem. But so I've got -2, 1, 1, and 5, 2, 3, 4, 5. Hopefully that's clear. -2, 1, and 5. Those are my x-intercepts, also known as my real zeros. Okay. Now, it's going to get a little tricky now, all right? Because now we have to worry about the end behavior. Before I do the local shape, I got to do the end behavior. So look at the power. 2, 1, 3. So the leader would be x to the 6th. That would be the leader. You would add all these powers. All right. Now, it's not just going to be x to the 6th. It'll be, x to the 6th plus blah, 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 blah. It's going to have several other terms. But all that matters when you're figuring out the end behavior is the leader. So this is the leader, or the leading term. Yeah. So do you remember x to the 6th from the last lecture? X to the 6th is even. The leading coefficient's positive, so that means both arrows are going to go up. All right, both arrows are going to go up. Now let's look at the multiplicity. All right. The 0 at 5 has multiplicity 2, so it's going to look like a parabola. Now, why did I pick this one as opposed to the upside down one? Well, look at the arrow. The arrow's pointing up. In the upside down one, the arrows are pointing down. That's why you want to put the arrows down before you decide which one it is. Okay. For the 0 at, I should probably go in order now. So next I'm going to go to this one. So it is a little bit of a double-edged sword. I'm telling you, when you fill out the table, it doesn't matter what order it's in. But then as soon as you go to graph it, the order matters. So, I'll leave that to you to decide. If you want to put these in order, then it's going to help you over here. So I have to go to this one next. 1 and multiplicity is 3. So it's going to turn like this, and it's going to zigzag through like a cubic. Yeah, it's going to look like a cubic. It's going to come zigzagging through like that. And then it's going to go way down. It's going to cross the y-axis somewhere. I don't care right now. If you really want to know where that point is, I'll tell you when I'm done with this problem. Because you might be going crazy, like, I want to know, where is that point? Please, don't leave me hanging. All right, maybe you care. All right, and then it's going to turn around. I don't really know where, but it's going to turn around somewhere, and it's going to come back towards -2. At -2, look at the multiplicity. The multiplicity looks like a line, and it looks like it's angling up to the left, so I'm picking that shape, and it's going to go straight through like a straight line. Essentially means that this piece of the graph locally is linear. It looks like a straight line locally. You might wonder why we use the word locally. It means if you lived there, if that was your neighborhood and you walked outside, you would think that you lived on the edge of a flat line, because that's what it looks like locally. If you got up in a hot air balloon and flew up into the atmosphere, you can look down and go, wow, I don't live on a straight line at all. It looks straight from where I was, but when I'm up here looking down on it, you realize it's not straight at all. Okay, so there you go. There's your graph. All right, and then if you really do care where this point is, all you have to do is plug in 0 here. So if necessary, or if you're just curious, so, if it's necessary or if you're curious, you can go ahead and plug in 0. This is not called a 0. This is called a Y-intercept. that drives some people crazy, that we don't treat the x's and y's the same. The word that I use when I'm talking about an x is not the same word that I use when I'm talking about a y. So that would be negative 5 squared would be 25 times 2. And then negative 1 cubed would be, again, just negative 1. Negative times negative times negative. And then all together, multiply that out, you get negative 50. I'm not actually going to count negative 50 squares. So for your y-axis, I just put a mark and call that negative 50. I went a little overboard on that problem because I wanted you to see the total picture. For the next few examples, I won't graph unless it's absolutely necessary. But so now you see. Yeah. Now you see what's going on. You could talk about the theorems very quickly. Should I talk about them just for a second? How many zeros does it have? 1, 2, 3. Yeah. What was the degree? 6. All right. So the theorem says that the function would have at most 6 zeros. Well, it does have at most 6. It has 3. And 3 is less than 6, so it's at most 6. Yeah. How about the turns? How many turns does it have? 1 down here, 1 here, and 1 here. Yeah. The inflection does not count as a turn, so only the ones that are actual U-turns count as turns. So it has 3 turns. How many could it have had? The degree is 6. It could have had 5, right? 6 minus 1 is 5. It could have had 5, but it didn't. It had 3. Okay. You always want to think about what could have happened, right? As opposed to what did happen. Sometimes what could have happened actually happens. That's why you always want to keep that in mind. All right, let's try another one. Find the real zeros and the multiplicity. For this one, I'll skip the graph and we'll just get right into the work here. Okay, so negative 12. Negative 12 has no x, so there's no real zero. Very important. I can't tell you how many times people practice, and they think they got it down, and then they look at that, and then they go, oh, the opposite of negative 12 is 12. Well, that philosophy doesn't work. This doesn't have a variable. So that is never going to be 0. That term will always be negative 12. So there's nothing you can do about it. All right, next one. X plus 3. What's the 0? You can just use mental math. Negative 3. You don't have to say x equals negative 3 when you're filling out the chart. I mean, I know that this is x. Okay. And then for x minus 7, 7. So those are your zeros. And then now the multiplicity. For 7, the multiplicity is 2. And for negative 3, the multiplicity is 1. If you don't see a power, it's a 1. And it's OK to have some blank rows. I guess that's it. Since I'm not going to graph it, there's not much else to do. Try another one. Sometimes we change the name of the function just for variety, but it doesn't change the process. So let's try 9x squared 2x minus 1, x plus 4 cubed. Okay. So same idea. We're going to make my little chart here. Zeros and multiplicity. I kind of have a standard size chart, even if you don't use the whole thing. So this time, the leading coefficient does have an x. So you're going to set that equal to 0. If you're good with mental math, you don't even have to write this down. You can just look at it and go, I see the answer already. I'm going to divide by 9. If x squared is equal to 0, you're going to take the square root. You could have done all that in your head, and you're just going to get 0. Yeah. What's the multiplicity? The multiplicity is 2, because it has an exponent of 2. So that one has multiplicity 2. The next one, 2x minus 1. Again, if you're good with mental math, you already know the answer. It's 1/2, right? But if not, that's okay. That's why you have a pen or pencil. So you add 1, divide by 2. And as soon as you get it, you go, oh, yeah, I knew that. Yeah, it was 1/2. Again, put that inside of one of my clouds here to indicate that you could have done that in your head. What's the multiplicity? It's 1. Okay. And then x plus 4 cubed. I think we're just going to do that one in our head. X plus 4 is -4, and the multiplicity is 3. There are higher multiplicities, but in general, it breaks down into evens and odds. So pretty much all evens look like parabolas. All odds look like cubics, with one exception. 1 looks like a line. So if it's even, it's automatically quadratic shape. If it's odd, it's cubic shape. But if it's 1, 1 is still technically odd, but it's linear shaped. So the odds, there are 2 possibilities. It's either going to be linear or cubic. Okay, let's go ahead and do some graphing now. And just keep this in mind. Oftentimes we make this chart just kind of off to the side. I'll put it over here in the margin or something, just to kind of guide us through the graphing procedure. You don't even have to make the chart, honestly. I mean, you have to in the homework, but that's about it. Once you've finished your homework, you've done these charts, 4 or 5 times, you'll never have to do another chart ever again. I know many of you are hoping if I pass this class, I never have to take math ever again. And that's also fine. Okay, so given the graph, identify the even and odd. Sorry, let me say this correctly. Identify the zeros with even multiplicity. Make sure I say it correctly. Multiplicity. And the zeros with odd multiplicity. So suppose you already have a graph drawn. And you got some zeros. So there's your graph. Identify the zeros with even multiplicity. So which ones are even? The only ones that are even, this one looks funny. Let's fix that one. The only ones that are even are the ones that look like parabolas or U-shaped. Now again, don't bother looking off the x-axis. When we're talking about zeros, we're talking about the x-axis only. So this is your neighborhood. Don't look outside the neighborhood. So you only have one zero with even multiplicity. X equals -1. That's the only one that's even. Yeah. The rest of these are all odd. Yeah. So odd would be this one. Let's see. 1, 2, 3, 4. -4 would be odd. I'm just going to list them out. 2 would be odd. Yeah, and 3, 4, 5, 6 would be odd. Okay. So that's all we know by looking at them, whether they're even or odd. I can tell you this. This is 1. Because it looks like a straight line going through there. Yeah. This one's also 1. And multiplicity there is 1. But this one you can't tell. Yeah? It's probably 2. Yeah, probably 2, but you can't tell. Every even multiplicity looks like a parabola. Remember in the beginning, the power functions, all the evens look like parabolas. That's probably a 2, but it could be a 4, it could be a 6. You know, it could be a lot of things. Yeah, it could be 4, it could be 6, it could be 8, it could be a lot of things. Yeah. And then the same thing here. This is probably multiplicity 3. Yeah, but there's no guarantee. I just know that it's not 1 and it's not 2. So it's probably 3, but it could be 5, could be 7, could be 9. You never know what it could be. So when you look at a graph or when you draw a graph, you should always think about what it is, but also think about what it could be, because you never know. You never know what's going to happen. In fact, you never know until you know. And then you know. You know? All right, let's do some graphs. I know I've been saying that for a while now, but let's actually draw a graph from scratch. Example 5. Graph f of x negative 3x times x plus 4 squared times x minus 3. Oh, I lost my focus. I lost my focus. Come on. Focus. There we go. Okay, so before I plot any points, let's just run through everything that we know. What would the leading term be? Again, we did this in the last lecture. So you look at the leaders, you look at the powers. This is 1. This is x squared, and this is another x to the 1. So this is negative 3x to the 1 times x squared times another x to the 1. So my leader is negative 3x to the 4th. Remember to add all the powers. So that's negative and even power. So that means both arrows are going to point down. So when I do my graph, the very first thing I should do is figure out which way the arrows point. I'll give you a hint on the test, in particular on the final exam. If you know that both arrows point down, you can automatically eliminate some of the possibilities if you don't have. I'm not going to make it so all the choices point down. All right, these graphs are typically done multiple choice. So you just draw the best graph you can on scratch paper and then just pick the only one that makes sense. All right, so I already know that both arrows are going to point down. Yeah. So let me just practice the end behavior notation. As x goes to negative infinity, y goes to negative infinity. As x goes to infinity, y still goes to negative infinity. So they both point down. All right, so that's our end behavior. Let's do our local behavior now. And I'm only going to make exactly the number of rows I need. So I have a 0 at 0, because -3 times 0 is 0, and the multiplicity is 1. Okay. If you want, I could peel that off and actually solve it, but I think it's better just to use your head. All right, x plus 4, what's the 0? What causes that to be 0? -4. What's the multiplicity? 2. Okay. And then x minus 3, what causes that to be 0? Well, +3, and the multiplicity is 1. So we don't have any cubics. It's all going to be lines and parabolas. All right, let's graph it. Let's see. I'm going to count by 2s here, just so that it makes the graph easier to read. All right, so I've got a dot at -4. I've got one at 0. And I've got one at 3. I know that both arrows point down. I know that -4 looks like a parabola. Touch and go, we call that. Touch and go, or touch and turn. Yeah, it's not crossing over. It's just turning and coming right back down. Yeah, that's because the multiplicity is 2. That's your local behavior. Now it's going to turn around. It just doesn't matter where it turns around. Just turn around naturally and then go through 0. 0, multiplicity is 1. So pass right through it like a straight line. All right. Turn around again. I don't care where you turn around. Just turn around somewhere reasonably. Don't go off the board. Don't go too low. You know, it's what we call Goldilocks. Not too hot, not too cold, but just right. And then come back down. Look at the last 0, the local behavior. 3 is 1. 1 means local linear, so it's going down again. And there you go. There's your graph. And I got the Y-intercept for free because sometimes the Y-intercept comes to you. You don't have to go looking for it. If you don't get it, then you might find it on your own if necessary or if you're curious. This problem I'm done. All right, so there you go. This is the graph of that polynomial function. Try another one. I don't know. Let's see. X times x minus 2 cubed times x plus 5 squared. What the heck? Let's do one more. No, we won't. I don't want to make it too messy. Sometimes I'm tempted to put in too much stuff here. We'll see how this goes. All right, the first thing you want to do is look for the leader. See if you can find the leader. Well, you don't have a leading coefficient, so you don't have to worry about any numbers, but you still have a leading x. So that's x to the 1. So your leader will be x to the first, x to the third, and x to the second. So this will be x to the 1 plus 3 plus 2, which is x to the 6th. All right, so this is technically a positive 1 and another even power, same as last time. So we have as x goes to negative infinity, this time y is going to go up to positive infinity. And then as x goes to positive infinity, y is still going to go up to positive infinity. So there's your end. Okay, or some people call it the long run. In the long run, this is what's going to happen. I often just do this in my head, and I know many of you will do the same thing. You just read the problem. You do all this in your head. This is you. This is your brain thinking about what power it is. Okay. I also like to make a little chart of the zeros and the multiplicity. Again, you can do this in your head as well. So you've got x. What value makes x 0? Well, 0. Yeah. What's its multiplicity? 1. Okay. What else do we have? X minus 2. What makes that 0? 2. Yeah, 2 makes that 0. If you plug in 2, you get 2 minus 2, which is 0. Multiplicity 3. Multiplicity is 3. And then for x plus 5, it's negative 5, and the multiplicity is 2. So I'm plotting my zeros. Again, I'm kind of doubling up my grid here, so every 2 blocks represents 1 unit. It just makes it easier to see, especially with the camera focus that I have here. You don't necessarily have to do that. You don't even have to use graph paper. But I mean, if you have graph paper, it's not a bad idea. Okay, at the end of the day, in the long run, both arrows are going to go up. Now, don't work from the middle out. Either go from the right over to the left or go from the left to the right. I do it the same way I read a book, left to right. Yeah, so negative 5. What's the multiplicity at negative 5? It's 2. So that's going to look like a parabola. All right, now go to the next one. 0. What's the multiplicity at 0? It's 1. So it's going to look like a straight line. Now, it's not exactly a straight line, but it's what we call locally straight. It looks straight. If you live there, you'd think you were straight. Yeah. Turns out nothing's really straight. Yeah. And then finally, we go to our last one. The 0 at 2, the multiplicity is 3. Now, this is the hard one. You have to kind of snake through it like that. And sometimes you have to adjust your grip a little bit. That's the tricky one. To try to make it look like a little shimmy shimmy. It kind of goes shwa right through that point right there. Okay. Here are some things I don't care about. I don't care how high that goes. I really don't. That's something we learn in calculus. So I teach calculus, come back in a future semester, and I'll teach you exactly how high that goes. Yeah. I don't care how low this goes. Yeah, I don't care, just whatever looks natural to you. So you do have a lot of artistic freedom here. Here is the only thing that I'm going to grade. I'm going to grade what direction the arrows go. So you better have the arrows going in the right direction. These questions are multiple choice. So just pick the one that has the arrows going in the right direction. And then I care about the x-axis. That's all I care about. So again, this is called the local behavior right here, and this is called the end behavior right here. So those are the things that I'm looking for when I grade your test. If we were in better times and we were together in the classroom, I would hand everybody a little, couple sheets of couple sheets of graph paper. It looks like this. You've all seen graph paper before. We would actually be doing this by hand, right? And I'd be walking around helping you do the shimmy shimmy and things like that. So, I hope we meet again someday. Let's do one more graph, and then we're going to have to change the tone a little bit and determine some characteristics of graphs without actually doing all of this work. So that's one of the things that we use theorems for in mathematics. I know it's a hard thing to see at your side of the screen over there, but when I teach a theorem, it's actually meant to make your life easier. So if you know the theorem, you have an easier time, and if you don't know it, then you have a much harder time. So one more for this particular presentation. So let's just do one more. Okay, so we got x minus 1 squared times x plus 2 times x plus 4. And there is no leading coefficient, so the leading coefficient would be 1, which you don't even have to write when it's 1. I like to write it, though. So again, what would your leader be? Uh-oh, did I screw up again? Oh, sorry. I almost screwed up. I'm glad we caught it now. These are both supposed to be squareds. Okay, those are both supposed to be squareds. All right, almost blew it on that one. All right, so the leading coefficient is 1, and then x squared, and then x to the 1 again, and then another x squared that I almost missed. So it's 1x to the 5th. All right. So that would be as x goes to negative infinity, y goes to negative infinity. I hope you're memorizing these, because it really is a disaster if you don't know them. And then as x goes to positive infinity, y goes to positive infinity. This is the easiest one. It's like a straight line, essentially, right? As you go left, the graph goes down. As you go right, the graph goes up. I mean, that's like the very first graph we ever learned in this class. A diagonal line, essentially. Now, I know it's not really a line. it's a wiggly curve, but at the end of the day, it thinks it's a line. Yeah. Okay. And then let's do our chart. Zeros in multiplicity. 3 zeros. Again, you don't really even have to make the chart unless I ask you to. It's not a bad idea, though, at least to have some kind of scratch work. Why don't I do something that I should have been doing all along? Why don't I put them in order? So what's the smallest 0? Well, the smallest 0 is -4. It's the opposite of this one. The multiplicity is 2. What's the next smallest 0? -2. Yeah, -2 causes that one. And the multiplicity is 1. Right. And then this one is +1, and the multiplicity is 2. And then the leading coefficient does not have an x, so you don't get that 0, 0, where one of these numbers is actually 0. All right. Let's see how this one goes. One never knows until you know. So there's -4. There's -2. And there's 1. All right. The end behavior, I'm going to call it the end. Right arrow goes up. Left arrow goes down. So it's kind of like a line going like this, yeah? From left to right like this. Now I put my zeros in order, which I really should make you do, but I really can't, because I can't in all honesty tell you that you're required to put them in order, because you're not. But because I did, you know, I get a little gift. Now they're already in order. My life's going to be a lot easier. So this one's going to look like a parabola. Now don't cross over, right? Some people will cross over and make a parabola, and I know what you mean when you do that, but it's not right. Just because I think I know what you meant, it doesn't work that way, all right? So then you got to turn around, and then the next one is linear. So turn around and come back up and make it look like a straight line. Now again, I don't care where you turn. Turn wherever you're comfortable turning, right? You can go way down here and then turn back up. All right, that's something for another class. Okay, and again, turn again. I don't care where. Come back down. Your last 0 is at 1. Its multiplicity is 2, so it should look like a parabola. There you go. Remember what I said earlier? Sometimes if it's necessary, or if you're curious, you want to know where that point is. It's not the origin. Sometimes it just comes to you as the origin, then you don't even have to go looking for it. But sometimes you have to look for it to find it, and I don't know what this is. All right, so let's find it. Yeah, the Y-intercept, just plug in 0. I'm not really talking while I do this, but maybe I'll now tell you what I did. I plugged in 0, then I got -1, and then I squared it. That gave me +1. 0 plus 2, that's a linear factor, so it just stays a 2. And then 0 plus 4 is a quadratic factor, so 4 squared becomes 16. And altogether, that's going to be 0 and 32. Now, I don't want you to redraw your graph and go, oh, shoot, that doesn't look anything like 32. This is what we do in this class. You just call that 32. Yeah? Or 0, 32, depending on the format of the question. Okay. Well, there you go. So that is the first part of 5.3, the graphing of polynomials. In the next segment, part 2, I will kind of turn it around the other way, and we'll talk more about the characteristics and things like that. And we might, you know, revisit some of these problems again, but from a slightly different point of view. Until we meet again, I will see you on the internet.